All right, let's see. Okay, I wanted the annotation, now I don't. So, okay, good. All right, so to kind of catch you guys up, so we just joined. We were talking about how we make the plots, and so I'll try to keep it brief because I don't want to go over stuff that you guys have already heard. But so the main thing with this is that we wanted to plot both the increasing substrate concentration and the velocity, just so we could see that curve, so that you can see it with increasing substrate concentration, you eventually reach, or you get very close to the Vmax. But then when you want to figure out exactly what the Vmax and the Km are, it's much easier to create this Lineweaver-Burke plot. And it's not foolproof. Some people don't like using it. But in general, if you take the reciprocal of your velocity, right, which you see here, and you take the reciprocal of your substrate concentrations and you plot those, it'll make a linear regression trend line so that you can grab the equation for the line and you can set either y or x to 0, because we know that the formula, if you look at the notes on Lineweaver-Burke, right, when we know when the trend line, we have our trend line generated from the substrate concentration reciprocal and the velocity of the rate of the reaction at those different substrate concentrations, we can see that the trend line, it will actually cross over the y-axis, and that's equal to 1 over the Vmax. And that when it crosses the x-axis, it's equal to negative 1 over the Km, right? So really what we're doing is we're associating this with the Michaelis-Menten equation and converting it into a Lineweaver-Burke equation that goes along with the Lineweaver-Burke plot of the reciprocal. Okay, so knowing that relationship, it makes it so that we can set y equal to 0 to get the Km, right? Because that means that we're going to be solving for x, because the Km should be here. And then for the Vmax, setting x equal to 0, because we know that the Vmax is equal to where the trend line or the line of equation crosses the y-axis. Okay, so if you set x equal to 0, you can solve for y, and if you set y equal to 0, you can solve for x. So essentially that's what we're doing. And so what I was showing them is that if you set y equal to 0 and you rearrange the equation, you can get the Km, or you can get, really what you're solving for is x, but then you have to keep in mind that you are going to have to retake the reciprocal of that equation, okay? So in order to solve for the Km. And then the main thing with the units is just making sure that you track the units. You plot it in micromolar, so you're getting micromolar for your Km. And then for your Vmax, when you set that equal to 0, right, when you set x equal to 0, it's just going to give you the b. That's the only thing that's left is the b intercept. And so if you take the reciprocal of that, you get your Vmax. And then these are just a series of conversions that you can go through to convert back to nanomoles per minute, and then moles per minute, which is really important, right? So you could alternatively multiply by 10 to the negative 9, and then getting our moles per second. And the moles per second are what we use to figure out what our K-cat is, or our rate of catalysis. So if you can go through problem one is really just setting you guys up to figure out how to construct a Lineweaver-Burke plot, how to interpret it, how to figure out what your Km and your Vmax is for any given enzyme by doing that kind of like an equation, and by doing that kind of analysis. The K-cat is really just interesting because what I was telling Cheyenne, Bailey, and Jamie is that when you're looking at the rate of catalysis, you're really just trying to figure out how quickly can one molecule of enzyme turn the substrate into product. Okay, and so when we talk about getting up to the Vmax, like you'll never actually achieve the Vmax. It's like a theoretical maximum velocity of the enzyme, but you can get very close as you increase the amount of substrate that's present. Okay, so what we're saying is that basically your turnover number, or your rate of catalysis when you've approached Vmax, is completely dependent upon how quickly physically that enzyme, that one molecule of enzyme, can convert substrate into product. Okay, so it's an interesting thing to think about in terms of, you know, no matter how much substrate you throw into the reaction, you're not going to increase the rate of catalysis. What's wrong?
Can you go to the sign up for Tinker again?
Okay, I'll do it in just a second.
When you're done?
Yeah. Okay. I gotta make breakfast for you guys too.
Because I accidentally deleted it and I need a new
the
account.
kids. Okay. I'll help you in just a second, sweetie. Okay, so for that one, that's pretty much it, right? The rate of catalysis, that means you have to think about how much enzyme you have there if you want to figure out what the actual turnover number is. And so with the rate of catalysis, you notice that we are using the equation that's up here where it says Kcat is equal to Vmax over the concentration of total enzyme. In order to figure out how much total enzyme you have to go back up to the information that you were given here, right, where it says the mass of the enzyme is 29.6 kilodaltons, and you have a 10 milliliter solution, which doesn't really matter what the volume is, but the concentration is 10 to the negative 9 grams of the purified enzyme. And so in order to figure out the rate of catalysis, you have to take the Vmax over the total enzyme concentration, which we know we have 10 to the negative 9. And importantly, when we say that we have kilodaltons, we know that daltons are grams per mole. So to have 29,600 grams per mole, you need to include that in the equation so that you can cancel out your units.